All right, so we already got that little box, which I hate. Come on, I hate you, box. All right, today we're going to start by multiplying. All right, some of these slides I got from Stephen Rudish, but they've changed a lot over the years since then. All right, so this is just a little on the side, and if you're not following this page, don't panic a bit. But you probably took complex numbers at some point in your life. And what's a complex number? Right, it's a real number plus a real number times I, which is the square root of -1. And if you want to multiply them, right, you multiply two of them out, you get a real part and an imaginary part. And so you can imagine a problem where you have 4 numbers as input, right, which are these, and your output is this number and this number, right? And you want to know, well, let's say multiplying costs $1, but adding's cheap. We'll give you an adding for a penny. Then how much does it cost to do this? Well, you can imagine $1 plus 2 pennies, it's $4.02. Right? Everybody with me here? Can you do it cheaper?
Yeah.
Do you say that? I mean, psychology-wise, I wouldn't be asking if the answer was no. But do you know how to do it cheaper?
Well, yeah, I was assuming, like, for example, A and C, you would just multiply A by itself C times.
Ooh, you're in big trouble. Wait for that one.
Okay.
Any other thoughts?
Can't you just do addition? Just add to the same number.
Yeah, that's what he said. Yeah, remember that. All right, so let's be tricky here. What we're going to do is we're going to first, you know, we need that, so you multiply that, and you need that, so you multiply that, and you know, we need this thing, so we do that, and everything is good. But now, let's be a little weird. Let's take the real and imaginary part of the first number and and add them together, and same with the second number and add them together and multiply, and then symbolically you get all those pieces, right? So then, if we note this piece and this piece, we already have computed, right? So we can subtract them, and we're left with this piece, which magically enough is what we wanted, right? And so what did that cost? Oh, I guess it went by, but it was 3 multiplications and some number of additions. Right? Everybody saw that? All right, so who cares? We saved ourselves a little bit of work. So let's go on to adding. Suppose these are 2 in-bit numbers. And pretty well anything I ever say, if you don't feel comfortable with bits, just translate in your mind digits, because it's all the same, right? You can work in any base you want. Here we have, you know, these are two digit numbers, and we want to add them, right? How much time does it take to add them?
N squared.
How do you add? We all did kindergarten. Maybe you know, Tom Lear is great. If you don't know Tom Lear, you should look him up. You know, you add these and carry, and add these and carry, right? You kind of go along. They're in things here. It's going to take you order in time. Everybody good? All right, so that's linear in the size of the input, right? You had n bits in the input, and the running time is n. That's linear. And you know, in big O, you know, it's sandwiched between some constant and another constant times. Everybody with me here? And you hate this box, so you can go away. All right, so what does big O mean, theta? Well, theta means that there exist 2 constants, and your function is squeezed between those constant times another function. Everybody remember big O notation? We're going to and ask lots of questions. All right, so can we add two n-bit numbers faster? Right? Can you add two n-bit numbers in square root of n time? Anybody think you can? No, why not? You gotta look at the numbers. We did this already, right? You gotta look at the numbers, right? You know, suppose there was an algorithm, you could do it, give the algorithm two numbers. If it doesn't look at all the numbers, there's some bit position it doesn't look at, right? If it gives you the wrong number, then you know that you have a bug already. Otherwise, you flip that one bit, right? And the algorithm didn't notice that you changed it, and it gives you the wrong answer in the other input. Everybody kind of follow that? All right, so those actually were added before I put the other lower bounds in, so maybe I should move these around. But we did the harder lower bound first, so that's kind of wrong. All right, so adding takes linear time in the number. No, it's linear time in the number of digits to write it down, not linear time in the value. Right? All right, multiplying. How hard is it to multiply if we have two n-digit numbers? We want to multiply them. Well, basically, if you remember multiplication, you kind of multiply like this, and all those numbers go down there, and you add them up. And what's the running time?
N squared.
N squared, right? Everybody got that? Right, N squared. Right, so it's bounded by some constant times N squared. Can we do faster for multiplying? No? Everybody think no? Well, you remember this whole, we're going to spend the whole day multiplying, so hopefully we can do something. All right? Okay, kindergarten. You guys asked about this algorithm. Right? One option is if we want to multiply a times b, we go a plus a plus a plus a b times. Right? What's the running time of this? Alright, time to multiply. It's linear time. Everybody good with that? It's faster than the high school. Why is kindergarten faster than high school?
Because one is the value and the other one is the digit of the value.
Right. Which one of these do you actually do when you multiply at home? Right? Isn't it counterintuitive that the fast one is the one that nobody does? Right? I want you to multiply these two things using the two methods. Which one do you want to use?
Multiply.
Hmm?
High school one.
Yeah, because this one here, you want to add this that many times? Rather not. Rather not, right? So this is kind of what we were saying before, right? B is the value, the size of the input is the log. It's the number of digits, number of bits, right? And so the kindergarten algorithm is actually exponential in n, right? As opposed to being n squared. Everybody got that? So kindergarten's not as good as the high school one. That's a good something, is right in the world. All right, so this is kind of, we looked at a linear time, a quadratic time, an exponential time. And so you should, I'm not going to spend much more time on this, but you should look at the back of the book, how to classify. I write down an equation. You should know whether it's exponential or polynomial or linear or log, or, you should just know those things. And you should know that quadratic is always going to be, eventually, for big enough n, is bigger than linear. An exponential is always bigger than a polynomial for big enough n. All right, so we've sort of said that multiplication is linear time, and adding is linear time, and multiplication is n squared time. So multiplication is harder. Are we done? Have we kind of understood everything here? Do we know that multiplication is n squared time? Do we know that? how do you know you can't do it faster? We came up with an algorithm. I can sort it in square time, right? Does that mean sorting has n squared time? No, you can sort faster, right? And in fact, you can add faster. In fact, you can add in n log n time. All right? We're not going to do that today, but we are going to add faster. If you want to add it in n log n time, then you can. I cover it in the grad class next term. You can come and take it. All right. So this is just says, we haven't proved that multiplying is harder. You might be able to multiply in linear time. Can you multiply in linear time? Yeah. If you can multiply in linear time, we'll give you a PhD. In fact, we'll give you more than a PhD. It'll be good. But hopefully we can do it in. All right. So the whole topic here is recursion, right? So you know that we're not done since we haven't gotten to recursion yet. Now, people for some reason have a hard time with recursion. And it's not so hard. And if you just listen to what we're saying on this page, life will be much easier for you. All right? Recursion's not so hard. And the key to recursion is that you get help from your friends and you don't micromanage them. You have a sense of what they can accomplish, you ask them and you trust them. That's all you have to do for recursion. Right? So I have some instance to my problem, right? There is some problem which is well-defined, pre- and post-conditions. I have an instance to it I need to solve. I take my instance and I break it down into smaller instances, and I give those smaller instances to my friends. And I trust my friends, they can solve any instance to the same problem as long as that instance is smaller than my instance, right? Because you can't get your friend to do something that's you can't give him the whole problem, or that's not fair, right? And you just trust that your friend will solve the smaller instance, and you don't, as I say, you don't micromanage him. He gives you back the answer, and then you take the answers that he's given you, and you somehow combine them to get an answer for your problem. Everybody kind of get this? And of course, if your instance is so small that you can't break it down any further, then just solve it yourself. Right? That's the base case. So, that's what we're going to do now. We have two numbers, right? Here's x, a whole bunch of n digits, and y is n digits. And my goal is to multiply these. And since I know recursion, it's nice to break your problem into pieces, I'm going to just simply cut my digits in half, right? So these will be the high order digits and the low order digits, right? Everybody with that? And so mathematically, what is x? The value x, right, was the value that you get from the b digits, right? And then you take the value from the a digits and you shift them and then you add. Everybody reasonable? Same with y. So symbolically, right, this isn't part of the algorithm, this is us doing math. We just multiply these two out. And what do you get? You get the low order digits down here, and then you get this multiplied and this multiplied, shifted once, right? And then you get the high order digits shifted twice. Everybody with us here? So now we're allowed to ask our friends any question that's smaller, right? There are two requirements to ask your friend. It has to meet the precondition, postcondition of the problem at hand, and it has to be smaller. All right? So what are we going to ask our friends here? Yeah, which smaller numbers? What numbers am I going to give my friend? B and D are fine numbers. They're smaller. All we have to do, my friend has to do is multiply them. So I just give my friend B and D, and what does my friend do? He just multiplies them. Do I care how he does it? No. I send them off to him, he multiplies them. That's it. Right? Now what do I get my friend to do? Maybe a different friend. Right? A friend can do this. A friend can do this. A friend can do this. Right? What happens now? I take my friend's answers, and what do? I add these two together. I shift these even further, I add. Right? How long does that take me? I'm just adding. How long does adding take?
Linear time.
Adding's linear, right? Takes order in time to add. Alright, so that's the algorithm. Right? If x and y only have one digit each, then I just multiply it myself. Otherwise, I break them into these parts. I get a friend to multiply b and d together, and another friend to multiply b and c together, and a and d together. I add their answers together and shift. I get another friend to multiply these together. I shift, and I add, and I return the answer. Right? That's the entire code. Everybody good with that? All right, so now we want to ask, let t of n be the running time of this algorithm as a function of n, where n is the number of digits. Right? And we want to know how fast t of n grows as a function of n. We want to know, for example, is it better or worse than n squared? Right? Anybody want to guess what the running time of this is? How many people like to believe it's smaller than n squared? How many people have no idea? Good. I like no idea. That's a good answer. Alright, so we have to build recurrence relations. One thing you will definitely have to do is recurrence relations. Alright, so t of n is the running time of solving the problem when you have an input of size n. Well, how much work is it to solve an input of size n? Well, I have 4 friends. Each one is given an input of size n over 2, right? Because I cut them in half. So each of them, how much work do they and all of their friends do? They do t of n over 2 work, right? And then how much work do? I do some linear amount of work. Right? Everybody kind of got that? We need a base case that t of, oh yeah, there it is up there. Right? T of 1 is a constant. Right? If I have an input of size 1, I just do it on my own. Right? So now we need to solve this. Everybody's solved recurrence relations like this? You do that master thing, right? Alright, so how do we solve this? The one way of solving it is you guess. The goddess comes down and gives you the answer, which is, I'm guessing that the answer is 2n squared minus n, and you plug it in and see if it works. Right? You plug it into here, and you see t of 1 is 1, which is 1. Oh, that looks pretty good. Right? You plug it into here, t of n, well, we're guessing that t of n is 2n squared minus n. Right? Then we plug it in here, and we get, you work it out, and it seems like it's true. Right? People kind of see that? So already we see the bad news that this is, that was the bad news. Right? People see this? Now, my feeling about this guess and verify method, what's the problem with it?
Take a while.
You have to guess. This is a non-deterministic algorithm for coming up with the answer. You have to be inspired by somewhere. So yeah. All right. So anyway, let's try to understand it better. Let the triangle mean the work that me and all of my friends do on an input of size n, right? And the circle means this is work that I personally do, right? I personally do in work, well, there's a constant here, but let's ignore it. In work, and then I have 4 friends, and each of them have an input of size n over 2, right? So we're saying that this is kind of equal to that. Everybody see what we're doing here? And
don't my friends have 4 more friends? Okay.
They have 4 more friends, right? They personally do n over 2 work, and they have 4 friends, and each of them has an input of size n over 4, right? N over 2, n over 4, right? And then it keeps going, right? They have 4 friends, and they have 4 friends, and they have 4 friends, and the input size goes down by a factor of 2 each time, and we bottom out and we get inputs of size 1, right? So we want to now look at this tree and compute the total amount of work. So here's just a table. Let's think about the ith level. Well, how many friends are at the ith level, right? There's 1 of me, and I have 4 friends, and they each have 4 friends, times 4 times 4 times 4. There are 4 to the I friends at this level. Everybody with me here? It goes up by a factor of 4 each time. What's the size of the input? Well, we start with an input of size 2. It comes down by a factor of 2 each time. My friend's input is half the size, his is half the size, hers is half the size. So the size of the input is n over divided by 2 to the I. Everybody with us here? Now, each of these guys does a linear amount of work, right? So if this guy is given input of size n over 2 to the I, how much work does he do? He personally does n over 2 to the I work, right? Are people with me here? Good? Everybody good? So we can say that the amount of work done at this level is, well, there are 4 to the I guys at this level, and each of them has an input of size n divided by 2 to the I, and hence does about n over 2 to the I work. Right? So this is the amount of work at this level. Now all we have to do is add these levels up. Everybody good? The top level costs n, and then the bottom level costs, well, what is the bottom level here? Well, it's kind of weird. I think we'll work on what this bottom level is right now. Here's a little trick. I don't know if you can read it in the back. That's useful a lot when you do these kind of things. If I have a to the log n, right here we have 4 to the log n, right? That's a weird thing. People have a hard enough times with exponentials, and people have a hard enough times with logs, but if you put them both in the same equation, it's just getting a little weird on us, right? Well, a, you can break it down into 2 to the log a, right? What does log a mean? Log a is the number that if you raise 2 to it, you get a, right? This is, in fact, just the definition of log a, is that 2 to it gives you back a. Right? People with there? And then 2 to the something raised to the something, well, those 2 things get multiplied together. Right? So it's 2 to the log a times log n. Well, then you can switch the order, so that's 2 to the log n to the log a. Right? And what is 2 to the log n? It's n. So we get n to the log a. Right? People follow that? So you can move things up, and as you move them up, you take a log of them, and you can, if they're already logged, you can bring them down. Right? So we bring this 2 up, this 4 up, it becomes log of 4, it becomes a 2. Right? And you bring the log down, and you get, this is actually n squared. Right? So we started off, this is n, the terms, we have all these things, it comes down to n squared. Right? So we want to add these up. All right, now, this has come back to adding, and a section of the math is you have to be able to add, and this is an example of where you need to be able to add. Right? What's 1 plus 2 plus 4 plus 8 plus 16 plus 32? Right? Going to try to argue that it's dominated by the last term. Right? So for example, here's proof by picture. You note that you sum up to say here, what's 1 plus 2 plus 4 up to 32? Well, the sum is double the 32 minus 1. Right? And if you sum up to 64, then it's double the 64 minus 1. Right? The sum, in this case, is 2 times the biggest term minus 1. And in general here, if you have some number r, and we want to know r to the 0, which of course is 1, plus r squared plus all the way up to r to the n, that's going to get dominated. It's going to be some constant times the biggest term. Right? People with me here? This is called a geometric progression. It's dominated by the biggest term. Which is the biggest term? Is this the biggest term?
Maybe.
Maybe. Depends on what r is, right? Right? If r is a half, then we got a half plus a half plus a quarter plus an eighth plus a 16th, right? And what does that add up to? That adds up to, if you start with a half, it adds up to 1, right? If you start with 1, it adds up to 2. Right? Everybody good with that? All right, so this is the chart we've looked at before. We want to know, I have some function f of n, and I want to know what's the sum of f of 1 plus f of 2 plus f of 3 plus f of 4. If f is a polynomial, then the sum is the number of terms times the last term. And now we see that if f is an exponential, then it's dominated by the biggest term. All right, so this is exponential increasing. It's dominated by f of n. And if it's geometrically decreasing, then it's dominated by, it's a constant, right? Dominated by the first term, which is a constant. So this is our table, which you should memorize, right? If your function, right, here is an exponential, right? If b to the a, you look here, b to the a, if b to the a is bigger than 1, right, then this is going to, who cares about that stuff, right? This is what matters, and it's going to be dominated by the biggest term, right? You might be summing 2 to the I, or b to the I, or summing 2 to the 2 to the I, right? It's going to get dominated by the biggest term. Everybody with that? All right. Oh, and similarly, if this thing is shrinking, if b to the a is less than 1, right? This is like 1 over 2 to the n, right? Or a half to the n. Then these, I don't care what you have here, this is going to make everything shrink down, right? If I have the sum of I to the 100, right? I to something that's bigger than 100 divided by 2 to the I, right? As I increases, first this is going to look really scary, but eventually, right, if you plotted this, it's going to go big, but eventually this is going to dominate, right? And if you ask for the area under this curve, it's going to be some constant. Right, people with that? You follow that? All right, so we're back to the sum. We want to say, does this sum, is it a polynomial or is it geometric?
How did you get from 4 to the power I to 4 to the power log n?
That was what we did, and the math that was down here, it was hard to see, right? We had 4 to the log n. Well, the 4 we can replace with 2 to the 2, right? Log n, which then can replace with 2 to the log n squared.
No, but why'd you write log n there? Because isn't it 4 to the power I? And then you, like, just above that? Like there's 4 to the power
Well, how do we get this log n?
Yeah.
You know, I'm surprised that I'd say it later on. Maybe I didn't. If we keep coming down by a factor of 2, then how many levels are there until you get inputs of size 1? Right, it's log n. So, right, in fact, this is, right, we start off with 1 input of size n, and then if this keeps coming down by a factor of 2, eventually we'll have 1 input of size, I guess then we'll have n squared inputs of size 1. Right, the number of base cases is going to be n squared, and each of them will be of size 1. Right? Does that make sense? So if you look at, compare this term with the next one, this is going up by a factor of 4, right? But it's going down by a factor of 2. So overall, it's going up by a factor of 2, right? So they're changing by a factor of 2 each time, and so it's a geometric sum, right? If it's a geometric sum, then what does it add up to? What do geometric sums add up to? Well, it might not be 2, but something times the largest term. In this case, you're right, because the r is 2. It will be 2, but in general, it's not 2. But it's some constant times the largest term. And what's the largest term now? Right? This one's n squared, and this one's n. Right? This is your biggest term, which is the number of base cases. So that's why we get that the total work here is n squared. People follow that? So it seems like a lot of work for nothing, right? And in some ways, it doesn't. Let me tell you a little trick here is if there's a fixed amount of work to be done, and I take some of my work and I give it to my friend, and he does it, well, you haven't decreased the amount of work, right? Somewhere you have to get some savings, or else there's no savings. You know, you don't get a free lunch. Recursion doesn't give you a free lunch. Everybody kind of follow that? All right. So this is basically the master theorem. All right, and we're gonna, in general here, we have T of n equals A. A is our number of friends we have. Each friend has an input of size n over b for some b. And I personally do f of n work. Right? People see these sort of, and then what do? We're gonna kind of go over examples, but you look at log A over log B and you compare it to C. Right? And let's do some examples. We'll come back to this table. All right, so we're wanting to evaluate that. Everybody, we have some constant A, some constant B, some function f of n. We want to evaluate this. Everybody kind of follow what we're doing? So we want to look at, these are the same levels as we had before. We want to know, start off with, what's the size of the input? Right, well my input is the size n, right? What's the size of my friend's input? N over b, and the size of his friend's input? N over b, exactly. And so at the ith level, n over b to the I, right? And after the bottom level of h, we got that. Everybody, so far so good? So let's figure out what h is. This is kind of what I didn't do last time, was figuring out how many levels there are. Well, let's try to find h. Can you read this at all? Sort of? B to the h equals n, right? Right? N over b to the h equals 1, right? So you bring the n over h up, you get b to the h up, you get b to the h equals n, right? And now we're solving for h, so what do? My son was just doing this last night in his grade 12 class. You take the log of both sides, right? You take the log of both sides, the h comes down. And now we're solving for h, so you divide by the log b, and you get h is log n over log b. Right? So that's what h is, log n over log b. Another way of writing this is h is log n base b. Right? You divide by b, you divide by b. Log n base b means how many times you divide by b to get to 1. I personally find base b confusing, and I I find it more, it's easier to say log n base whatever you like divided by log b. Right? It's the same thing. All right, how much, if this is the size of their input, how much work does each of them do? Well, I have an input of size n, I do work f of n. So if they have an input of size n over b to the I, they do f of that work. Right? Everybody kind of got how much work do they personally do? All right, now what are we going to put here? How many are there? How many friends do you have? Right? Well, how many of me are there? There's one of me. Right? A friends, a squared. Right? We have a to the I guys at the ith level. Everybody good? So now we want to know what's the total work. Oh, how many, what's this key about this number here? It's how many base cases are there? Right? It's a good number. How many base cases are there? Well, a to the h base cases. Right? What's h? H is log n over log b. Right? So how many base cases? A to the log n over log b. Right? Now, what do I don't like? I don't like a base here of a, and I don't like a log n at the top. Both of them make me nervous. So, but I can bring the a up, and it becomes a log a. Right? And I can bring the log n down, and it becomes an n. People with me there? So I get n to the log a over log b. So let me tell you right now, you need to memorize this equation. I hate memorizing, but this is a fine one to memorize. How many base cases are there? They're n to the log a over log b. Right? You either have to be able to drive it quickly, or you need to memorize it. It's just one of those realities. I don't make people memorize too much, but this is one of them. Everybody got that? So that's how much work, how many base cases there are. So now how much work at each level? Well, if you have 2 to the I friends and each of them does this much work, then this is how much work is done at the ith level. Right? At the top level, there's only one of me and I do f of n work. Right? So the top work is f of n. The bottom work is we have n to the log a over log b friends, right, base cases, and each of them does a constant amount of work because they have a constant size input. Everybody good with that? So now what do we want to do is we want to add this up, right? Generally speaking, that's the adding it up. Generally speaking, this, let's go back to, it's geometric and it's dominated by the biggest term. Right? Which is the first term or the last term. Right? So, generally, this is dominated by either the top case, the work done at the top level, or the work done at the base cases. Right? Everybody got that? That's why you have to memorize this amount at the bottom. Right? This you have, this you memorize the equation from the a and the b, and the answer is the bigger. Right? People got that? So, do I got any? Oops. No. Come on back. You can do it. Don't die on me. No. I hate you, little box. I hate the little box. All right. Come on, computer, you can do it. You can do it. No, we don't want you over there. We want you to go back. Okay, here. All right, so study this box up. This is a box that's in the back of the book, and it's also in, if you go to Math 0 section, the steps, this is there, right? I want to solve T of n is this recurrence relation. Remember, A is what? The number of friends. B is what? Every input goes down by a factor of B. F of n is what? It's the amount of work I personally do. Right? How do you compute it? Well, you compute log A over log B, right? And you compare it to C. Why? Oh, so what is C? We're assuming f of n is into the C with some log factors, poly log stuff that we ignore, right? F of n is basically into the C. So we want to compare the into the log A over log B is the number of base cases. Into the C is the work at the top level. We compare them, right? And if log A over log B is smaller than C, then it's dominated by the top level, right? And if log A over log B is bigger than C, then the answer is the number of base cases, right? And if they're equal, then we leave that until later. Everybody with me here? I think we're going to do this one later too, but just as a warm-up here, the difference is my friend's input is not a beat the size. I make it maybe one smaller or two smaller, right? And do you want to do this? This is bad news. You're going to get exponentials, all right? We're going to do this when we come to Tara Hanoi, all right? All right, so we did all that work for nothing. We got n squared time. So, but it wasn't all that a waste of time. It got us working up on recursion, and it got us working up on recurrence relations. And now let's see if we can go faster. All right, so this was the algorithm we had before. Remember, we were given x and y. We broke them in x into a and b, and y into c and d. And we had 4 friends. Right? And we got our friends to work. And remember the key numbers in the recurrence relation, the number of friends, which is 4, and how much smaller our input is, which was n over 2, which was half, right, which was a 2. The other number was how much work do I do, right? The amount of work I do is linear, so in C is 1. Right? Now, of these numbers here, which ones can we get rid of? Can we improve on? Is it possible that I do less than in work? No. One, it's not likely. And 2, would it even help? What happens if I did a constant amount of work? Would that solve our problem? No, because remember it was the number of base cases that killed us. Right? The f of n didn't even come into it. Right? So what do we have to do? We either need fewer friends, or we have to do more damage to our input. Everybody right there? Are we likely to make our input even smaller? Cut it in smaller pieces than 2? Well, in the grad class, that's what we're going to do. We're going to cut it into smaller than 2 pieces, more than 2 pieces. Right? In fact, we're going to cut it into log n pieces, and that's how you're going to get the log n over the n log n running time. But right now, we're going to stick to cutting into 2 pieces. So what do we need to do instead? We need to kill one of our friends. Anybody want to volunteer? All right. So how? Oops! I should have asked you. I should have not brought that box up. I should have asked you. How are we going to kill one of our friends? And the answer's already up there. 5 minutes, all right. Man, these hour classes go fast, eh? So, remember the Gaussian trick at the beginning? Right? That's what we're going to do again. Remember we have a numbers A, B, C, and D, and our goal is to compute, we need to compute the high order stuff, the middle order stuff, and the low order stuff. Right? And we were doing it with 4 friends, and we want to know, can you do it with 3 friends? And I guess it was Gauss. You know about Gaussian elimination stuff? Figure out how you can do it. So what we're going to do is we need this number, so there's no way of getting around it, you compute it. Right? You need this number, no way of getting around it, you compute it. And now, how do we do the middle stuff? Well,
Do you make one friend do the entire thing?
Somehow, but how? Right? Let's add these two together. Right? This is the high and the low order term of x, and you add together the high order and the low order terms of y. Right? And adding is cheap. Right? I can add. I do the adding. And then I get one friend to multiply those two together. Right? It's a weird thing to do, but we do it. Right? 2 additions, 1 multiplication. And if you multiply this out symbolically, this is what you get. Right? People with us here, how you do that? Now, anything you recognize? You know, these we know, so we can subtract off. And by some miracle, what we get is what we want. Right? Everybody see that? So, we subtract off what we have and we get what we want. And we're done. Everybody good with that? Now, if you're panicking about this, right? This is weird little math and you're never going to see it again. Alright? It's just, you know, we're trying to, it's an example. Alright, so here's the algorithm. Right? If my inputs are of size 1 bit each, I just multiply them. Otherwise, I cut them into 2 pieces each. And I get one friend to multiply the high order stuff, one friend to multiply the low order stuff. I add the high and low order of the x and the high and order of y, and I get a friend to multiply them together. I subtract off what we calculated before. Then I shift all these appropriately and add, and we got the answer. Everybody get this algorithm? We just saved a friend. So, one friend died. Right? Everybody good here? So, this is what we did before when we had 4 friends. If we kill off of a friend, does the running time of the algorithm go down by 25%? Is that it? Do we get a 25% savings?
Yes.
More.
All right, well, let's see. We kill that friend. We just got a 75% savings. Right? But then we kill those friends. And we get more savings. Right? And then we kill those friends. And we get more savings. Right? You see what I say? It goes all the way down. So let's go back and calculate what our running time is. Right? There's 1 of me, 3 of my friends, 3 of them, right? And we go all the way down. Right? So at the ith level, we have 3 to the I friends now. Right? Before we had 4 to the I, but now we have 3 to the I. Let me assure you, 3 to the I is smaller than 4 to the I. Right? The size of our inputs go down the same as they did before, down by a factor of 2 each time. Right, everybody good? So now the number of cases here is still log n like it was before, right? They come down by a factor of 2 each time. There's log n levels, and the number of friends is 3 to the I, so it's 3 to the log. It's 3 to the log n. Right? People with me here? So you bring the 3 up and the log n down, and we get into the log 3. And into the log 3 is into the 1.58, right? Which is bigger than linear, but better than n squared. All right? So it's dominated by the number of base cases as before, right? So now how do you evaluate these things? Right? I calculate how much time for the top level. It's n. C is 1. Right? People with me here? Right? How many base cases? You should memorize. N to the log A over log B. Right? What's log A over log B? Well, this one's a little harder to do, but it turns out to be 1.58. Right? Then, which of these is bigger? Well, it's dominated by the base cases, so that's the answer. Everybody good? And we have a savings. And so what's the conclusion for today? Is kindergarten algorithm for multiplying is exponential. Grade school is n squared. Some Russian dude is into the 1.58. And I kind of lied to you here. There's an extra log term, right? So how does your computer multiply? It does it in log n time. Right, which is pretty fast, right? It's faster than you would ever dream to be able to multiply, right? Everybody good? All right, so have a good evening, have a good Tuesday. Wednesday we'll keep doing recursion. Friday we'll keep doing recursion. Monday we'll have a test.